couple pictures right now that describe a couple scenarios that you should be pretty familiar with. And then we're going to take those diagrams and kind of translate them into something that's a little bit different, a little bit new that we haven't seen before. First one has object number 1. We'll give it a velocity to the right of, let's say, 10 meters per second. Doesn't matter what the mass is. It's moving to the right. It collides with object number 2 that is stationary. Let's say they stick together and they head off as one and directed to the right after the collision. So we've done this before, right? Car number 1, object number 1, ball number 1, whatever, moving to the right, collides with ball number 2 that's at rest, and then they head off together as one to the right. How do we do this? How do we analyze this problem? It's not new. I'm not looking for some new thing that you're, coming up with on your own. What is it?
PI equals.
Yeah, it's just PI equals PF, right? We would say in this case, M1 V1I plus probably 0, right? Because object number 2 is at rest, equals mass total times VF. That is if they stick together, right? Not rocket science, unless it's a rocket colliding with something else, in which case it's rocket science, but it's pretty easy, right? That would definitely be our column 1 type question, right? Where it's doable. Not necessarily everybody going to get it right. Everybody makes mistakes, right? But it's certainly a doable question. What about this one? What about object number 2 moving downwards at a velocity of, let's say, 8 meters per second, colliding with object number 1 that is stationary this time? So it's different object moving. Still, 1 colliding with a stationary. How would we deal with that? The same thing, right? PI equals PF. This time we'd say 0 plus M2 V2I equals mass total times BF. Right? Another column 1 type question where it's doable by everybody. We all make mistakes, but we all have a fighting chance, at least, at a question like that. Right? What if we see this? What if we saw this problem, where ball number 1 or object number 1, whatever it is moving to the right at a velocity of 10 meters per second, just like in that first problem over there. And ball number 2 is moving downward like this with a velocity of 8 meters per second, just like in the second problem right there. They collide, they stick together during the collision, and they head off as one. Where are they going to go? That's my first question. Where are they going to go? Where's the wreckage or the combined mass 1 and 2 going to go? Diagonal? Which way? Like general vicinity. I'm not looking for like 27 degrees west of whatever. Just general vicinity. Which way?
South.
Yeah, somewhere south and east. Where exactly, we'll figure that out later on, right? Somewhere down there. We know that's the case because, well, we know that momentum is conserved. So if we had momentum to the right before the collision, we have to have momentum to the right after the collision. If we had momentum down before the collision, we have to have momentum down after the collision. So it has to be down and to the right. Where exactly? Not sure yet. Somewhere down in that vicinity. Well, how do we analyze this? I purposely colored them the way that I have here. The first problem is black. The second problem is green. The third problem is black and green. What we have to do in a question like question number 3 here is do exactly what we did in the first question and exactly what we did in the second question, and then combine them. We have to break this third problem up into an x component and a y component. Remember, x is this, and y is this. Remember that? Mm-hmm. We have to break it up into the x component and the y component. The x component is going to look like this. Well, I'll just write it out since it doesn't want to copy for me. It's going to look exactly like this problem. How come? Well, because if we're looking at just the x component, object number 2 isn't moving on the x-axis. It's only moving on the y-axis, right? When we're dealing with the x-axis here, the x component here, just pretend whatever's on the y-axis doesn't exist. If whatever's on the y-axis doesn't exist, then we would say object number 1 moving at 10, object number 2 is at rest on the x-axis. It's this problem right here, right? Now, let's do the y component of it. What's the y component look like? You probably figured this out by now. Pi equals Pf. We would say 0 plus M2 V2I equals M total times Vf. Why is object number 1 0? Because what? Is object number 1 at rest? Looks like it's moving at 10 meters per second, but it's at rest on the y-axis. Good. It's moving, but we're not paying attention to the x-axis, and that's where it's moving, right? We're focusing on just the y-axis. So everything that's not on the y-axis is 0. This problem, this third problem that we're working on so far, is really just question number 1 and question number 2. Now, we're not quite done. Usually what we'd end up solving for here would be the final velocity. But we've got 2 of them. Which one do you want? Which one do you want? Both? But isn't there only... How can we have 2 answers? Riley? Yes, we're going to combine it into a vector diagram, triangle, right angle vector diagram, triangle, and then we do our thing. This is physics 20 now. Like, what we've done so far definitely isn't physics 20, but what we're about to do is just physics 20. It's like week 4 of physics 20. We solved for an x component of the final velocity. We solved for a y component of the final velocity. And then the final velocity is just this. Got to solve for the angle as well, because velocity is a vector, right? Need a direction. Notice I put the angle at the beginning of the diagram. You guys remember the rules for drawing vector diagrams in Physics 20? Your vectors have to be drawn head to tail to head, doesn't matter. Head to tail to head, whatever, right? The tail of one vector, tail of the second vector has to be touching the head of the first vector there, right? And then your resultant is drawn from start to finish. That doesn't look like my first diagram, right? That's not a vector diagram. This is what we call a situational diagram. Just shows you what's going on. The vector diagram, which is where you do your real work, your vector diagram has to be drawn head to tail. Now, how would you find the value of v there? Like, we're not going to solve for this because we don't know what masses are, and we can't get a number for this right now, but if we could, how would we solve for v? Yep, right? Yeah, it's Pythagorean theorem, right? A squared plus b squared equals c squared. Or c is equal to the square root of a squared plus b squared. Or we're calling c v. V would be the square root of x squared plus y squared. Good? And we'd say theta is equal to the inverse tan function of opposite over adjacent. This would be my opposite side, and this would be my adjacent side. Okay? Ring a bell? Okay, let's do an example here that has some real numbers and kind of maybe solidifies the concept that we just did here. Number 1. 1,200 kilogram car traveling north at 10 meters per second collides with a 1,500 kilogram car traveling west. Draw this out. This is not, what I'm drawing right now is not my vector diagram. This is my situational diagram. It just helps me to visualize what's happening here. I got to write down my givens, so I might as well do it in the form of a diagram. Car number 1 collides with car number 2. 1,500 kilogram car, 12 meters per second. 1,200 kilogram car, 10 meters per second. They collide like this. We'll say it's at point X. Where are they going to head after the collision? Where are they going to go? Yeah, north and west. We want to avoid saying northwest because northwest is 45 degrees, right? So north and west, where exactly? It might be 45, but coincidental if it is. Let's do our X and Y components now. We have two objects, so this is what it looks like. M1 is 1200. What's V1I? Tyler, what's V1I there? How much of that 10 meters per second for object number 1 is on my x-axis? Right, correct. So I'm just going to cross that out, or you could put in a 0 for it, or you might have even not even wrote that term in because you knew it was 0 when you were writing it down, right? That's okay. M2 is 1,500 kilograms. What's V2I? What's V2I? Yeah. Yeah, almost. Almost. Yeah, let's make it negative 12. Total mass is 2,700 kilograms times VF. Solve for VF there. And I believe it was negative 6.666. No. Yes, I believe 6.666. 7 meters per second. You notice what we did there, right? Object number 1, 0. We were paying attention to the x-axis. If it's not on the x-axis, it's 0. Well, this time, if it's not on the y-axis, it's 0. So let's write this out. Pi equals Pf again. M1 V1I plus M1 V1I plus what? Enrique, how much of that 12 meters per second for object number 2 is on the y-axis? Because that's what we're doing now, right? How much of that 12 is on the y-axis? Got it? None? Yeah, 0. Yeah, it's okay. Like, you're about to say it. Like, just have confidence to say it, right? And if you're wrong, oh well. 0, right? It's all on x-axis, which was important for this, but not for this. M1 is 1,200 times V1I is 10. Total mass is 2,700 times VF. And I think when we solve for VF there, that one works out to be 4.44. Which one's the correct answer? Yeah, neither. You know what the thing that's going to tick you off, though? You get a multiple choice question on a test. Those are both probably going to be there, right? Like, you're going to work through it, you're going to get a number, you're going to see the number there, and you're going to be like, oh, I got a number that's listed, that must be correct. Like, finish the question, and then if you see your answer, go with it. But don't just go with it because you see a number that you got partway through a question. Okay, we're not quite done, but we are done the physics 30 part. Let's do the physics 20 part of it now, which ironically might be the hardest part for some people, the vector analysis. Let's redraw this situational diagram as a vector diagram now. We have 6.66 to the left. I know that's left because it was negative. And we have 4.44 up, positive. Where am I going to draw theta in here? Position 1, 2, or 3? Where does theta go? Position 1, 2, or 3? Yeah, it's 3. Always goes at the start of the diagram, right? Now you could have drawn this. You could have drawn this like this, right? Would that have been okay? Mm-hmm. Sure, that's still drawn head to tail. Just means your angle would be the complement to the angle that I get, right? If I get 30 degrees, you would have got 60, right? That's okay. We just have to define the frame of reference, right? Like, where am I right now? I'm 2 meters from the front of the room. Well, I could also say I'm 6 meters from the back of the room. Don't they mean exactly the same thing? Two different numbers, but they mean the same thing, right? That's exactly what we have here. I'm measuring my angle from the west axis. If you do it the other way, you'd be measuring it from the north axis, that's all. Okay, let's do this. Let's say V is equal to the square root of 4.44 squared. I'm going to go second function, 4.4444 squared plus 6.66667 squared, 8.01. I think it was 2 digits though, actually. Yeah, let's round it to 2 digits. And theta would be the inverse tan function of opposite over adjacent. You guys comfortable with opposite and adjacent? That's probably grade 10 when you did that though, eh? Like opposite, adjacent, hypotenuse. The adjacent side and the hypotenuse both touch the angle. So one of these is adjacent and one is hypotenuse. Well, the hypotenuse is easy because it's the longest side. So this is hypotenuse. Well, then this one must be adjacent. The one that's not touching the angle over here is the opposite side. So we're saying the inverse tan function of opposite over adjacent, 4.44 over 6.67. Let's figure that out now. I'm just going to make sure my calculator's in degree mode. Do you know the nice little check for that? Math class, I think you want to be in radian mode, right? How many people are in Math 30 right now? You guys got to be in radian mode? Back and forth? Okay, physics, we're always degree mode, always. Okay, nice little check. Every time you do a question, Physics 30, or at least the first question of the day in Physics 30 involving angles, not a bad idea just to go sine 90. And if it equals 1, you're good to go. If it equals 0.899, then you got to switch it. So I'm good there. I'll say the inverse tan function of 4.4444 divided by 6.6667. Oops. Gives me 34 degrees, this would be. Now, how do we express that? Is it 2 meters from the front of the room or 6 meters from the back of the room? Is it 34 degrees what of what? North of west is correct, yes. Here's what you can do. Draw little crosshairs there. Say, like, look, this red vector is going north and it's going west, right? Mm-hmm. Was it north of west or west of north? We're measuring our angle from the west, right? It's touching the west. But then we're going north from the west, right? So we're going to express that as north of west. If we had have done it this way, that would have been 56 degrees, yes. But it would have been 56 degrees measured from the north, but west from the north. Or 56 degrees west of north. West. Yes. Is that okay? Like when you take a step back from this and look at the method, follow the recipe, it's like, I don't think they're all that bad. I really don't. But man, they're a lot of work. Right? It's like 3 questions in one. Like the questions that I gave you before the break on worksheet number 3, like for every one of these questions you have to do, it's like 3 of those questions. And so they're not bad, it's just the amount of work involved. All right, we have, what I want you to do right now is worksheet number 4. For now, we're going to do questions 1 to 3 on worksheet number 4. Okay, let's drop what you're doing here now and take a look at question number 1. It says a 1,000 kilogram car traveling south 1,200 kilogram car traveling east. If we have a south and an east, that's two different dimensions, right? South and east. Okay, well, we're dealing with two different dimensions, two different axes. We know we're going to have to do x and y components. We know we are. So let's draw it out. Let's draw a situational diagram here. Car number 1, we'll say, is going to the south, 1,000 kilograms and 20 meters per second. And another one going to the east. We'll call this car number 2, 1,200 kilograms and 20 meters per second. We could have easily reversed the names of these, called this one number 1, this one number 2. Where is it going to go after the collision? After they stick together? Probably down here somewhere. Not probably down there somewhere, for sure down there somewhere. So now we do our x and y components. I'm going to say 0 plus m2 v2i. How come I said 0? Claire, where did that 0 come from? Right, it's going down, right? And that means that it's not on the x-axis at all. We're only paying attention to what's on the x-axis. Everything else is 0. The 2 is on the x-axis, but the 1 isn't, so it's 0. Equals mass total times VF. Let's sub in our numbers here. M2 is 1,200 times 20 equals, the total mass is 2,200 times VF. And VF worked out to be, for the x component, that is, 10.909. How many people got that? 10.909 meters per second. Yep, good. Now let's do the y component. This time we're going to say, all right, Calvin, what's M1 V1I? We have numbers for that, right? We're dealing with the y-axis, so it's going to be 1,000 times negative 20 downwards. Calvin, I meant to ask you the next one, actually. What's M2 V2I for the y component? 0. Right. We're dealing with the y component here, and if it's not on the y-axis, it's 0. So we're going to say it's 1,200 times 0. It's moving 20 meters per second, but not on the y-axis. Equals, what do we got? 2,200 times VF. 1,000 times negative 20 is negative 20,000. Divided by 2,200 is negative 9.09. Now we just redraw it. We got 10.909 and 9.0909 meters per second. A couple people asked me, at this point, did we just drop the negatives? Yes. At this point, you just drop the negatives. The negative up here was to indicate a direction. We're indicating the direction down here by the arrow that we've drawn. We don't need a negative to show direction anymore. Okay, we've got a picture that shows direction. We're going to solve for V there, and we're going to solve for theta as well. Where am I going to draw theta? Position 1, 2, or 3? 1. Yeah, it's position 1. That's at the start of the diagram. By the way, is that a legitimate vector diagram? Yeah. The black arrows are drawn head to tail. The resultant is drawn from start to finish. That's fine. We're going to say V is the square root of 10.909 plus squared, that is, plus 9.09 squared. Gives me 14.2 meters per second. And theta is the inverse tan function of opposite. What's the opposite, 10 or 9? Megan, what's the opposite side here? Is it 10.9 or is it 9.09? Yeah. Yeah, that's the opposite side of the triangle, good. And the adjacent side is 10.909. That works out to be, for in degree mode, 39.8 degrees. Now remember, we draw little crosshairs right here. This vector is going south and it's going east, right? But is it going south of east or east of south? Well, we're measuring the angle from which, are we measuring it from the east or from the south? It's touching the east, right? It's touching the east. So it's measured of the east. Well, it must be south of east, south from the east. So that's our answer, 14.2 at 39.8 degrees south of east. Anybody put 14.2 at 50.2 degrees east of south?
I did 50.17 east of south.
Is that okay?
Yeah.
Sure it is, right? I'm 2 meters from the front of the room. I'm 6 meters from the back of the room. Same answer, right? They both describe exactly where I am. Okay, let's finish up this worksheet for homework tonight. Up to the end of number 3. Remember, you also have a quiz number 4 tomorrow, and your lab that you've had for the last week and a half is due as well.